Welcome back to the deep dive. Today we're pulling apart a really fascinating technical problem. We're going deep into the infrastructure needed to power the next generation of AI development.
That's right. We're talking about giving autonomous AI agents their own virtual desktop environments.
And we're not just talking about a terminal window here. This is the whole setup.
Exactly. A full GPU-accelerated Linux desktop. It's got UIs, browsers, code editors, all the tools a human developer would actually use.
And the goal is to stream that to multiple users at once with what? Gaming-grade speed?
Gaming-grade speed, but enterprise-grade stability. That's the challenge.
Okay, and this is where the paradox comes in, which is what makes this so interesting.
Yeah.
The team we're looking at, Helix ML, they needed a solution that was robust, low latency, great with video.
And they looked at the usual suspects, right? Things like VNC or RDP.
But they realized the best tool for the job wasn't designed for remote work at all. It was actually designed for streaming high-action PC games.
Precisely. They landed on a protocol called Moonlight, which originally came from NVIDIA's game stream service.
So the real core of this deep dive is, how do you bend a protocol that was built to stream, like Cyberpunk 2077, to one person?
And make it serve a multi-user collaborative session for an AI agent. You're taking a private stream and trying to force it into becoming a shared workspace.
Okay, let's unpack that. Before we get into the wild protocol stuff, we have to establish why. Why does an AI agent even need a full desktop sandbox?
I mean, we're all pretty used to AI just living inside our IDEs, right?
Yeah, as a little coding assistant. So why the massive overhead of a whole virtual desktop?
It really comes down to autonomy and visibility.
Visibility. You mean so the human managers can actually see what it's doing?
Exactly. If you want a truly capable agent, it has to operate visually. It needs to see the screen, navigate complex GUIs, click buttons.
Stuff that doesn't have a clean command line interface.
Right. Think about legacy systems or proprietary software, or even just weird web-based dashboards. The agent has to be able to handle those.
And the human needs to be able to watch that process, to audit the work.
You got it. You need the agent to run the task. But you, the human manager, you need to confirm the steps, validate the state, maybe even debug a visual error.
Which brings us to the architecture. You need the agent's environment running on a powerful server with a great network connection.
Yes, a GPU-equipped server, but the human manager might be connecting from, the hotel Wi-Fi.
Or the beach, as they say. So you need a rock-solid stream coming to their client no matter what.
That's the core challenge. And the goal, really, is that users won't just manage one agent. They'll manage a whole fleet of them.
So you need a system that can reliably stream, a dozen of these active environments at the same time?
At the same time. And each one is a full Linux desktop in a container with its own GPU running real tools like Claude or Zed or VS Code.
Okay, that makes the low latency requirement completely non-negotiable. You can't have lag if you're trying to debug a UI interaction.
You just can't. The typical lag you get with older solutions like VNC just doesn't cut it.
So let's talk about that choice. VNC and RDP were on the table. Why go with something from the gaming world instead?
Well, the trade-offs were just decisive. VNC and RDP, they were built for office work, right?
Yep.
Typing in a document, moving files.
Low bandwidth, pretty static screens.
Exactly. They just fall apart when you throw high-motion video at them. Your input lag can be like 200 to 400 milliseconds. It just feels sluggish.
Whereas Moonlight, by its very nature, is built for high-motion, high-resolution video.
It has to be. It was engineered by NVIDIA to stream games at 60 frames per second or even higher. Latency is usually down between 50 and 100 milliseconds.
That's a world of difference. It feels like a local machine.
It really does.
Yeah.
Plus, it's built around hardware encoding, H.264 or H.265. So the server's GPU is doing the heavy lifting of compressing the video.
Taking the load off the CPU, maximizing throughput. Okay, and to get this all working in containers, they're using a pretty specific stack. You mentioned Wayland and Sway. Why not the old standard, X11?
That's a great question, and it's crucial for containerization. X11 has all sorts of security and multi-user issues when you try to share a GPU between containers.
Right.
Wayland, and specifically the Sway compositor, just offers better security isolation and much better rendering efficiency. Sway is perfect for a headless, scripted environment.
So the full stack is a Docker container running the desktop on Sway and Wayland,
Using the GPU for rendering and encoding.
and the server piece of the Moonlight protocol is handled by something called Wolf.
Yet Wolf is an open source C++ server For the Moonlight protocol, it's the engine inside the container that captures the desktop and sends out the stream. It's mature, battle-tested, and most importantly, it lets you interact directly with the protocol layer.
Which I'm guessing became very, very necessary.
Oh, absolutely necessary.
Okay, so it sounds elegant, but this is where the problem really starts. This is where it gets really interesting. The fundamental design mismatch.
Yes. The protocol's whole assumption is a private, isolated experience.
One user, one game.
One user, one game. A client connects, the server spins up a new private session just for them. If you and I both try to connect to the same thing in standard apps mode,
We get two totally separate instances.
two separate containers, two separate running apps, which is great for gaming. You do not want my inputs messing with your single-player game.
Of course not. It's
Yeah.
built for isolation. But Helix's need was the complete opposite.
The complete opposite. They need multiple users to see the same shared session. The agent has a fixed identity, it has files open, it's in the middle of a task.
So if two managers connect, they have to see that one single fixed state.
And if one manager clicks a button, the other one needs to see that happen instantly.
That is a massive, massive contradiction. And then there's the other problem. They needed the agent to just start working on its own, not wait for a user to connect.
Right. When a job gets assigned from like a Kanban board, that forced them into their first and most complicated workaround. They called it the kickoff hack.
A kickoff hack. Okay, walk me through this. So the API had to pretend to be a user.
It had to pretend to be a client, yes. Since apps mode needs a client to start anything, the Helix API had to basically trick it.
How does that even work? What's the mechanic there?
So when work was assigned, the API would make a WebSocket connection to the Moonlight web adapter.
So it's a ghost client.
It's a DOS client. It triggers the server to spin up the container, start the desktop, and crucially, it would set the video parameters like lock it to 4K at 60 FPS.
And then what? It just disconnects.
And then it immediately disconnects.
That is so clever, but it sounds incredibly fragile. I mean, your whole infrastructure is relying on an API pretending to be a web browser.
The complexity is enormous. You're maintaining a client-side thing inside your server-side API just to trick a protocol. And it only solved the auto-start problem.
Right. It didn't solve the sharing problem.
Not at all.
So the agent is running, the desktop is up, but if a real user connects, what happens?
The protocol just falls back to its old assumption. The new connection triggers a second totally separate container to spin up.
Oh no. So you'd have two different code editors open, both thinking they were the same agent.
And you get massive state confusion. The hack worked to get it started, but the fundamental single-user constraint was just this permanent anchor on the whole architecture.
They were fighting the protocol with every single line of code.
Every line.
Okay, that's an architectural nightmare. You build this complex, fragile hack just to start the session, and the main thing you need, collaborative viewing, is still broken.
It was completely unsustainable. It just proved that protocol assumptions run deep. They really needed a feature that was built for shared screens from the ground up.
Which brings us to the actual solution, Lobbies mode.
Exactly.
So this sounds like it was designed for this kind of thing. Was this built by the core Wolf developers?
It was a pretty recent addition, actually, driven by the gaming community's need for things like split-screen multiplayer or shared co-op sessions. It addressed the exact problem they were facing.
So how does Lobbies mode fix this? How does it get them multi-user state without the crazy kickoff hack?
It just completely flips the flow. First, the Helix API talks directly to Wolf's own API to start the container. No more pretending to be a browser.
Okay, so that's cleaner already.
Much cleaner.
Yeah.
And second, this is the magic Lobbies mode, creates a fixed identified session, a lobby.
And multiple clients can join that same lobby.
Exactly. Whether it's a browser client or a native Mac client, they all connect to the same session.
So everyone sees the agent's true state. If one person moves a window, everyone sees it happen in real time.
It solves both problems at once, the auto start and the multi-user access. It's the single source of truth they needed.
That's fantastic. Another benefit you mentioned was the fixed resolution.
Yes, the resolution is pre-configured when the lobby gets created. It's a bit less dynamic than apps mode, but that stability is essential for a shared view.
You want pixel-perfect consistency for everyone watching. Okay, so Lobbies mode is the future, but shifting core infrastructure is never easy. What are the stabilizing bugs they're dealing with right now?
There are two big ones, and they're both usability killers. The first one is broken input scaling.
What does that mean for the user? What's the impact of that?
Okay, so imagine the lobby is configured for a big 4K display.
Yeah.
You connect from your smaller laptop screen.
Right.
Wolf correctly scales the video down so you can see the whole desktop. But the mouse coordinates don't always scale with it.
Oh, so you click on a button.
And the input actually registers, 200 pixels off to the side.
That's not just annoying, that breaks everything. If you're supposed to be helping the agent by clicking a specific icon, the whole environment becomes unusable.
It's an immediate, I can't use this moment. It completely destroys trust in the system.
Yeah, that's a showstopper. And the second issue?
The second one is specific to Apple hardware,
Mm.
video corruption. Sometimes when you connect from a Mac, the video stream just gets garbled. It's likely an H.265 negotiation error, and they're still hunting that one down.
And you mentioned the fixed resolution was a trade-off. Before, each client could set its own resolution dynamically. Now it's preset.
Right. They have to choose a resolution. They joked it could even be iPhone 15 vertical before the lobby starts. But you make that trade-off to guarantee that the agent's environment is identical for every human manager. Consistency is more valuable than flexibility here.
So to bring this full circle, let's trace the final cleaner architecture. Lobbies mode is in place. How does the signal get from the agent's desktop to my browser?
Okay, so the whole thing is orchestrated by the Helix API, which talks to Kubernetes to manage the containers.
The GPU-backed containers.
Right. Inside the container, you've got the Wayland desktop. Wolf captures that desktop's output and uses the GPU to start encoding it with the Moonlight protocol.
And if I'm watching this in my web browser?
That stream goes from Wolf to an adapter, Moonlight Web, which basically bridges that proprietary protocol into the standard WebRTC that browsers can understand. The key is that the foundation real GUI apps in Wayland with gaming-grade encoding gives you performance that older protocols just can't touch.
This whole journey is such a perfect example of modern engineering. What are the big takeaways from having to stretch a gaming protocol like this?
The first, and I think the most profound lesson, is that protocol assumptions run deep. I mean, even when a protocol has the raw performance you need, low latency, great video, the core behavioral model, like one app per client, can be an almost insurmountable wall.
And the kickoff session hack was the direct result of hitting that wall.
Which leads right to the second lesson. Workarounds just compound complexity. That hack was clever, but it was fragile, with code debt. Waiting for the right feature for Lobbies mode was the better long-term path.
That choice between a fast hack and a clean solution.
Always a tough one. And the third lesson is just that cool cross-pollination of tech. The solution they needed was already being built by the gaming community for shared screen gaming.
High-demand gaming problems end up solving enterprise problems.
All the time. And finally, it really shows the value of open source. The Wolf maintainer added Lobbies mode because the community needed it. That's an agility you just don't get with closed-source tech.
So what does all this mean for the future of how we interact with these visual AI agents?
It means the performance bar for remote interaction has just been permanently raised. As agents get more visual using real browsers, real IDEs, that low latency and high quality that gamers demand, it's not a luxury anymore.
It's a fundamental prerequisite.
It is. The user experience is now intrinsically linked to the streaming architecture.
And looking ahead, once Lobbies mode is stable, once those bugs are ironed out, that's when the real potential is unlocked. We'll see native clients, and that whole kickoff hack will be deleted, and you'll have seamless management of a whole fleet of agents.
And here's a final thought to leave you with. As these agents demand more and more visually simulated environments, the plumbing, the streaming architecture, becomes just as vital to success as the AI model itself. So how will the demands of managing a fleet of visually working AI agents change how we think about remote desktop protocols entirely? Will they just drive everything closer and closer to gaming grade standards until that simply becomes the new norm for all enterprise collaboration?